Okay, so this is Wednesday's class for my pre-cal students, grade 11 pre-cal. And we've hit the point of the course where we're done the curriculum and we're getting started on stuff for next semester. But while we're at it, we're kind of reviewing this semester as well. As I was pointing out, I handed out something that I always hand out at the beginning of my semester 1 introductory calculus course, because I've got some kids who took grade 11 the year before, or maybe they're in grade 12 now and they haven't thought about grade 11 math for months and months. So it's nice to kind of review. There's actually some grade 10 stuff on here too, like slopes and intercepts and stuff like that. But starting at number 3, if there is anybody here who is planning on retesting factoring, there's some nice factoring practice for 3, 4, and 5. And then you hit number 6 and it's like, wait a minute, we didn't really do that in grade 11, so let's show you how to do that. If you are, I didn't mean to close it. That's what I meant to do. If you remember, we learned that if you have a squared term minus another squared term, we know that it factors like so. Why does that work? Well, it works because if you go back and multiply this, if you FOIL a plus b times a minus b, you get first times first. Outside times outside is minus a times b, which is minus ab. Inside times inside is b times a, which is the same as a times b. And last times last is minus b squared. And notice those middle terms cancel. So anytime you have what's called a difference of squares, which is what you call the thing on the left here, you get what's called conjugate pairs. And that's a very important skill for factoring. You learned it for the first time in grade 10, and then it popped up again in this course, and we've had a whole bunch of questions where you had to factor a difference of squares. One thing that's interesting, though, is you can do something pretty similar to a sum or difference of cubes. So if you had, for example, a cubed plus b cubed, you can factor that. It factors to a plus b times a squared minus ab plus b squared. And if you had a difference of cubes, you'd get a minus b times a squared plus ab plus b squared. And just like you could prove that the difference of squares things work, you can prove that this works as well. You can multiply that out. Take a times all 3 of those terms. Take b times all 3 of those terms. And when you collect like terms, you'll be left with nothing but a cubed plus b cubed. Everything else cancels. You can kind of see why if you want to try running it through for yourself. But that allows us to do questions on this worksheet I gave you, like what number is it? Number 6? So you might want to jot that rule down, because that's how you do all the questions in number 6. So that's a type of factoring that we run into in calculus from time to time that now you should know how to do. So let's just do maybe a quick example. Suppose I noticed that I had 8x cubed minus y to the 6, and I wanted to factor it. Well, is this thing a perfect cube? Yes, it is. It's 2x times 2x times 2x. Is this thing a perfect cube? Yes, it is. It's y squared times y squared times y squared. So factoring it would lead to 2x minus y squared times, and then follow the template. It's the first thing squared then it's the two things times together, but notice the sign gets changed to a plus. So change the sign to a plus, and then times these two terms together. And then the last term squared. And when you square a negative, you get a positive anyway. And there you have it. Those two things are equal. So there's more for you to practice on those on number 6, on the worksheet that we gave you. And then, let's see, let me go back to that worksheet. So number 1 and 2 is all about grade 10 review. I don't know that you need to do much of that, but again, if you kind of scan through this and go, ooh, I could use a refresher on how to do this. Like, for example, do you remember how to find an equation given 2 points? Maybe we should quickly review that. That's not something that popped up much in this course this year, did it? Did it ever come up in this course where we had to make an equation given 2 points? I can't remember. But you did it in MEAP a lot in grade 10. So let's just maybe do the A question here. Let's do 2A. Determine an equation of a line through each pair of points. So if you have a pair of points, how do you find an equation? So let's maybe do one from number 2. Here, we'll do that one. We'll go, I have an untitled page I can put it on right here. Go away. Okay, determine an equation of a line through each pair of points. Okay, so how do we do this? Well, remember that there are 3 different ways I can give you an equation for a line. 3 different forms for an equation for a line. There's standard form, which is nice to look at, but not particularly useful. And then there's the more useful slope-intercept form, where that's my slope and that's my intercept. Certainly that's the way we like to graph things. That popped up in our last unit when I was graphing straight lines again. But does anybody remember the third way? The third way doesn't get used very much, but it's actually really useful, and it's how we'll do number 2. Anybody remember this? That's the one I'm going to use. It's called the point slope form of a straight line. And what it's showing you is that as long as you know the slope, which you'd call m, and any point with a coordinate x1 and a coordinate y1, if you know the slope and you know one point, you can make the equation of the line. So here's 2 points. Who remembers the formula for slope? Well, slope is just difference between the y values over difference between the x values, which in grade 10 you probably wrote like this. Right? Does that bring back memories? So let's apply that to these 2 points. So the slope between these 2 points, we'll call this one the first point, and we'll call this one the second point. So it's the second y coordinate minus the first y coordinate, and the second x coordinate minus the first x coordinate. So that slope is going to be 12 over 4, which is 3. Now, it doesn't matter which of the 2 points I pick next. I'll pick the first one, and I run it through that form of the equation. So it's y minus y1 equals m times x minus x1. So the y1 coordinate is -4, so that's y. Now I do this little trick. You've seen me do this before. Minus -4. Rather than write it like this, I like to do it like that. It's kind of one less step of simplification. In my head, what I'm actually doing is I'm writing the minus negative by taking this negative and turning it and rotating it by 90 degrees and turning it into a plus. So I even kind of say it that way. Slope is 3, x minus -2. That's how I try not to lose track of negatives. So easy to do. How many half marks and single marks have you lost over the years because you lost track of a negative somewhere? So frustrating. All right, we're done, sort of. That's an equation, but it did say it wanted, what did it want from me? Oh, it wanted this form, right? It wanted slope-intercept form. That's slope-intercept form. So I would multiply that through and know that that's a 6, but the 4 has to move over and join it. So there it is, slope-intercept form. So that's what they're looking for. By the way, can I point out that choosing to use this point here instead of that point is completely arbitrary. As once I knew the slope was 3, it wouldn't have mattered if I'd have used the other point. So y minus 8 is equal to 3 times x minus 2. So if I use the point 2, 8, there's the 8, there's the 2, I'm going to get the same answer because 3 times x is 3x, 3 times negative 2 is 6, but when I add the 8 to it, it'll work no matter what. I mean, it should work, right? It's the same 2 points on the same line, right? Or those 2 points are collinear on the same line. So there's how you do number 1 and 2, slopes and equations of lines. After that, it's basically factoring review. And for anybody here, again, who wants to retest factoring next week when we do our retest day, this is some good practice for you. For 3, for 4, for 5, but then look out, 6 is our new skill. All of those involve cubes. Keep in mind though, what is the first thing you look for when you're factoring? You always look for a common factor first, right? So a couple of them I can see from here. There's common factors you can work with. Okay, then I'm going to skip 7 for now. I'll do the factor theorem lesson maybe tomorrow. So I'm going to skip 7 for now. And let's look at number 8. This is something we did earlier this year, right? We looked at simplifying rational expressions. This was one of our outcomes. I think that was A4. Simplifying rational expressions and finding their non-permissible values. Right? So let's take a look at 8A. Simplify this and state any restrictions on the variable. Oops. Keep hitting the wrong thing. Okay. All right, so who remembers how to find the restrictions on the variable? What is my non-permissible value here? Anybody who wanted to retest the chapter 6 stuff, A4, this is a nice little review for you. So, don't all shout it at once. What's the non-permissible value? -2. X can't be -2. Why? Because then I'd be dividing by 0. But what's interesting about this is that x plus 2 is a factor of this expression. So I can simplify the expression by factoring the numerator. What 2 numbers times to make 6 add to make 5? It's 3 and 2. And then this factor divided by itself cancels. So this thing simplifies down to x plus 3, again, as long as x is not -2. And what I find interesting about this is that one way that you can show that these two things are exactly the same as each other, that this expression and this expression are identical, is to pick any number you want as long as you don't pick -2. Pick 0 if you like. What if x was 0? Well, then this would be 6 over 2, which is 3. Put a 0 in for x, you get 3. That should work for any number in the whole universe, obviously except for -2, because you can't divide by 0. And because that works, what you can show is that if you had the graph, let me get Desmos happening here. If you had the graph of y equals x plus 3, it'll look exactly the same as that big complicated looking thing. What was it again? It was x squared plus 5x plus 6. Or no, wasn't that? Oh, there were minuses involved. What was it again? That's how good my memory is. Oh no, they were both pluses. Convinced myself they weren't. Plus 5x plus 6. And if you were going to use this program to make fancy graphs, if you want to divide, just highlight everything and then hit the slash button, and that's divide. And then what was it again? It was x plus 2. Notice it's the blue line, it's the red line. It's the blue line, it's the red line. So those two things are equivalent. They're the same thing. There is, however, one minor difference between these two graphs. What's the difference between them? Well, on the red graph, on this equation, x can be -2. There it is right there. But when I try to graph this one, looks the same. Oh, it's got a hole in it. Doesn't exist there. So that's one of the reasons why we have to be able to divide polynomials and simplify those divisions, is because we have to look for places on our graphs where perhaps it doesn't exist, where there's a hole in the graph. So that question, oops, there we go. So that question, number 8, was all about factoring, simplifying, and then stating what the non-permissible values are. So this is a nice little A4 review, if anybody was going to retest A4. Okay, moving along. Number 9. This is A5. Can you add, subtract, multiply, and divide rational expressions? Can you simplify stuff like this? So we're going to do something. Okay, I don't want to do the question for you, so I'll just make one up. Suppose I had. Let's make one up. So let's do an example for one like number 9. Suppose we had 1 over x minus 3 plus a third all over. I don't know. Let's see. What is the other one? What am I comparing to here? Just over an x. Okay, fine. Over an x. Good enough. Okay, let's simplify that. How do we do it? Well, remember that if I'm going to simplify this, I need this thing here to have a common denominator, right? You can't just go out and add 1/2 and 1/3. You have to change that to a common denominator of 6. So what's my common denominator between this denominator and that denominator? It is 3 times x minus 3. So I'm timesing top and bottom here by 3 times x minus 3. So on the left one, that's going to leave me a 3. And on the right one, it's going to leave me an x minus 3. And instead of dividing by x, I'm going to change that to a multiply. And remember that when you're in fractions, dividing by a number means timesing by its reciprocal. And look at how that's going to turn out. That's going to turn out quite nice. I'm going to end up with 3 plus x minus 3, which is just x. The denominator is going to be 3 times x minus 3. And then I could simplify my answer back, but very often these kinds of questions, it'll just say, just leave it in factored form. And if you're thinking, why would I just leave it in factored form? Well, one of the things that we're going to be approaching or talking about a lot in calculus is, what do the graphs of these things look like? So if this had actually been an equation So I've just proven that this thing here is equivalent to this thing here. And when I first started, and I looked at this thing, I would have no idea what this graph looks like, none whatsoever. But I can actually be very sure I know what that graph looks like. And you should too. You know what y equals 1 over x looks like. Looks like this. So what does this minus 3 do to it? I'll give you a hint. If you know what this looks like, what does that minus 3 do to it? The minus 3 does the same thing to this parabola that it does to this reciprocal graph. So what does that minus 3 do to it? It shifts it 3 units to the right. So this asymptote here, which is my non-permissible value of 3, is now there. Now, what does this 2 do to x squared? It makes it narrower. Remember that? Makes it skinnier. So what would this 3 do to this one? Now, careful. You have to kind of think about this a little more logically. In fact, maybe we could even use Desmos to kind of help us a bit. And there's that stupid keypad. I don't know why it keeps popping up. Go away, keypad. Okay, let me close that one. Suppose I have y equals 1 over x. What if instead of a 1, this was a 2? Oh, look at that. It's like the arms are getting farther apart, but maybe the better way to think about it is its y values are being doubled, tripled, quadrupled, sextupled, which means that the y values are going up faster compared to the x values. So if that's what the top number does, what will happen if I put a bottom number down here? It'll behave the opposite. So instead of the arms moving outward, a number down here will move them inward. 2, 3, 4, 5, 6, 7. Whoops. I lost my divide. There we go. There we go. In fact, if you want, put a slider on there. And then you can play with it as you like. So when it's 1, it's like a normal one. And as the number gets bigger, it gets closer and closer in like that. So, like I was saying, I know that behavior, so I know what this thing looks like. I could give you a quick sketch of it, no problem. This minus 3 moved it over, and this 3 kind of tightens it closer to the asymptotes. Would I have had any chance of looking at this thing and knowing what its shape is? Not particularly. So that's kind of one of the reasons we learn how to do this stuff. So we can turn ugly equations into equations that, oh, I know what that looks like and I know how it behaves. Okay, so anyway, that was number 9. Number 10. If anybody wants to retry or retest next week rationals, this is one of the things that you learned how to do in rationals, rationalizing the denominator. So let's do one of these together. Let's pick a tough one. Let's do B. Okay. So, how do we rationalize that denominator? Well, this kind of goes back to what we were talking about here. What are those things called again? Conjugates. I'm going to multiply this thing by 1 so that it doesn't end up having any radicals in its denominator. But my 1 will be the conjugate of this. So it's going to be that. All right. right, what does this look like? Well, it's going to be 9 times the two things on top, which isn't going to do very much other than put 9s on these things. But the denominator is where the real action is. I know that when I have a plus b times a minus b, I won't get a middle term. I'll just get a squared minus b squared. So because I know that, think of this as the a, think of that as the b. So think of that as the a, that is the b. I know that my denominator will just be x plus 3, get it? A squared minus x. So that's now going to be just 3 on the denominator because those things cancel. And 3 can divide into those two things. So it's going to be a final answer of 3 times root x plus 3 minus 3 root x. And I can't combine that anymore. But I have a much easier looking thing to work with than I had a minute ago. Okay, so that's a very important skill that we did this semester, rationalizing the denominator. It's going to pop up quite a bit in the intro calc course. And again, if there's anybody thinking of retesting it because it didn't go great the first time, or you want to try to improve your mark, you can kill 2 birds with 1 stone. Get ready for next semester and prepare for your retest by trying the rest of them at number 10. So that takes you to number 11. Number 11 is kind of what we were just talking about a minute ago when I said, how does this change affect the look of a parabola? And it's like, okay, well, you should be able to figure that out. What does a plus 2 do to it? Well, it's going to move it up 2, etc., etc. Notice, however, that this is a little more complicated than we did it, because notice they leave things in function notation. We'll talk more in the next couple days about function notation. So if the notation here confuses you, you can skip this question, but give it a try and see if you can make it work. So that's 11, a little bit of quadratic practice. 12, again, this is function notation, which we'll talk about in an upcoming class. That's the one handout that didn't make it from the print shop, is a review of what function notation looks like. I wouldn't worry about number 13 for right now. You can ignore that one. And 14 for sure. Actually, this finite difference method of finding equations is not something we ever do in calculus, so you can skip 13 and 14. In fact, 14 doesn't even work. I did have some students try number 14 last year, and it turns out that the answer key is way. In fact, this one, I think this is a typo of some sort. A works, but B does not. Okay, and I'm not going to worry about these word problems. They're kind of physicsy, so we'll skip those for now. So there we go. So there's the first section. There's a whole bunch of stuff that's review, a couple of things that are kind of new ideas, like factoring sums and differences of cubes. The answer key is right there. Now let's move on to division. Okay. We do number 1 here the same way we do, what question was it on the last page? Number, was it 8? Yes, we do number 1 on this next page the same way we did number 8 on the previous page. I know that x plus 3 is a factor of x squared plus 8x plus 15. So I just factor it and cancel, and then state what my restriction is. X can't be negative 3. And I think B works the same way. I think C works the same way. Then I get to number 2. How do we do that? Well, let's see what we can do here. Let me go back to, oops. That's what I want. Let me go back to my page where I can write. Okay. If I was asking you to divide 72 by 12, chances are most of you would notice, oh, 12 is in 72, right? It's like if I had my times table up on the wall, 72 would be in the 12 row. So you just go, well, you might just know off the top of your head that 72 is 6 times 12. And so you just go, well, it's 6. But if I gave you something like, say, 720 divided by 12, wouldn't you just sort of approach that the same way? You'd kind of think of it as, well, I'll factor the 12 out of here, and then there's my answer. My answer is 60, right? Well, that's basically what we did when we did, that division right there, right? We factored and then canceled, and what was left over was my answer. But what would you do if I asked you to do 720 divided by 13? You'd reach for a calculator probably, right? What if I don't let you have a calculator? When was the last time you had to break out your long division algorithm? Anybody? Okay, so let's do it. How many 13s in 720? All right, well, what do I do first? I'm seeing some looks of absolute horror. There's people who haven't thought about this since grade 5 or 6. Okay, so what's the first step? Well, you have to kind of skip count. How many 13s are there in 72? Well, how about this? If this was a 12, I know this would be exactly 6. So it's probably 5. And one of the things that's great about this algorithm, this technique, is that it's very self-correcting. I put a 5 up here. And now, what did I just do? Well, I just divided, right? I went 72 divided by 13. Okay. And then what's the next step? Well, I have to now multiply 5 by 13, which is 65. And then I have to subtract that amount to figure out how much is left after that. Remember that? So 12 minus a 5 is a 7. And then do you remember what your next step is? You bring down, right? Now you do the same thing. You skip count, and once again, it's going to be 5 again, right? 5 times 13 is 65. And I have a remainder of 5. Now, you have options at this point, right? Back when you first learned this in grade 5, I think you just went R5, right? Remainder 5. Okay, that's fine, but we have more grown-up ways to deal with remainders than that. Can I point out to you that maybe the best way to deal with this remainder is to think about this not as a divide, but as a fraction. It's an improper fraction right now. What would it be as a mixed number? Any ideas? Well, it'd be 55. And what? Right, this remainder, 13ths, right? Exactly. So that's probably the best way. The answer here is actually 55 and 5/13. If I'd have wanted a decimal, I could have put a decimal there, kept going zeros, and kept on rolling until I found the repeating pattern, which I believe for 13ths is either 6 or 7 digits before it would start to repeat again. 13ths aren't pretty. But do we remember the steps? And do you remember how to handle answers? Can we do that? Okay. Then let's go back to this question here. But instead of dividing by x plus, what was it, x plus 2? Let's divide by x plus 1. Now you're probably thinking, well, I'll try factoring first. And you should. Just like when I give you this divide, you'd go, well, I'll try just seeing if I can do it with my times table. But once I can't, I go to my long division algorithm. So this is going to be called polynomial long division. Because this is not a factor of that. So first thing I'm going to do, I'm going to kind of compare the steps. So the first thing I'm going to do is I'm going to rewrite it in division form. Notice that the bottom ended up here, And the top ended up in this division bracket. So that's the first thing I'm going to do. Okay. Maybe I should rewrite the actual, what was it again? It was 13 into 720. Okay. What was the first step over here again? I figured out what I had to times 13 by to get as close as I could to 72. And it turned out the number I was looking for was 5. Okay, I'm going to do the same thing here. What would I times x plus 1 by to get as close as I can to x squared? And there's people probably already going, well, this is totally different than that because this has a bunch of adds in it. What, I can't express 720 as 700 plus 20? Of course, it's still the same idea. So once again, what would I have to times x by to get as close as possible to x squared? I'd have to times it by x. And then what did I do in the next step over here? 5 times 13 is 65. X times x plus 1 is x squared plus x. Okay, what was my next step over here? I subtracted. I've forgotten what I got. 7, right? So what am I going to do over here? I'm going to subtract. I put a little bracket around it to remind myself I'm subtracting both of those terms. So that's x squared minus x squared and 5x minus x. What was my next step after I had that 7 as a remainder? I brought down the 0. Made it a 70. Well, I'm going to bring down this plus 6. Then what did I do? I repeat the process till I'm out of things to divide by, right? In this case, it's only one more step. How many 13s go into 70? 5 of them. How many x plus 1s go into 4x plus 6? 4 of them. And repeat the process. 5 13s was 65. 4 x plus 1s is 4x plus 4. I subtracted this. I'm going to subtract this. Six minus 4 is 2. 2 is my remainder. And again, this isn't grade 5, so you can't just say R2. You would say the answer is, what did I say we did with this answer again? We made it 55 and 5/13. This is going to be x plus 4 and 2 over x plus 1. And that's the answer when I divide. And that's long dividing with algebra. All right. Want to try another one? All right, let's try another one. Let's do a bigger one this time. So it takes more steps. What if I wanted to do, let's see. Let's go to your homework. What if I wanted to do that one, 2a? Move out of the way, you. Okay, there we go. There we go. Okay. So what was my first step again? Write it the way you traditionally write division. I should give myself a little more room here. Okay. Now what? what do you times x by to get to x cubed? Times it by x squared. And then x squared times x plus 1 is x cubed plus x squared. What was my next step? Which is exactly the same step I did when I did long division with numbers. Subtract and find the remainder. So that cancels, and then 2x squared minus an x squared is another x squared. And then what do? Bring down the 3x. All right, what do I have to times x by to get to x squared? I have to times it by x. X times x plus 1 is x squared plus x. 3x minus an x is 2x. Bring down the 2. And how many x plus 1s go into x plus 2? 2 of them. Oh, what does that mean? When that happens to you when you're long dividing, what do you say? You say there's no remainder, right? So that's it, there's no remainder. So I can say that x cubed plus 2x squared plus 3x plus 2 divided by x plus 1 is x squared plus x plus 2. You know what else I could say? So that's my answer for this question. But notice I could also say, let me write this better. Let me write that answer over here. Because now, imagine a quick cross multiply. I can also say that x cubed plus 2x squared plus 3x plus 2 is equal to this thing times that thing. And now, I just figured out how to factor that cubic. There's its factor. I could try to even factor this thing, but I don't think that quadratic factors, does it? The two numbers times to make 2 and add to make 1. No such thing. So that's it. Factored. Okay, so that is algebraic long division. Is it the only way to divide? No, there's a shortcut way. I'll show you that tomorrow. First, try doing the long divide a few times. So that takes us to, let's see, number 2, where all of those should divide quite nicely. Same with number 3. Actually, I think pretty much all of these on this page are just divide practice. Yep, there we go. So there we go, divide practice. So I'll let you have some work time then. You can play around with these questions, and I don't really care where you start. If you want to try right away into the divides, or if as we went through this previous page, you were like, oh yeah, I should maybe practice my factoring, or practice my rationalization, or my fraction work, then by all means you could do those first. Okay? So all right, I'll give you some work time for this little booklet here, and tomorrow we'll show you the other way you can divide pieces of algebra. All right, I'm going to stop my little video.